Hello again. We are now going to do one more interesting exercise, which is postage stamp problems. So this is also known as the coin problem or McNugget problem. It actually involves trying to see whether you can combine integer valued stamps in a certain way, such that you are asked to compute the largest postage that cannot be attained. And for that, we are going to pick relatively prime numbers. So consider 3 and 5 cent stamps. How do we model any number of 3 and 5 cent stamps and their numeric values? In regular expression land, there is no counting other than through unary methods. So lo and behold, if you write a regular expression of this kind, RE of 111 plus 11111 star, it is all the stamp values in a string sense. So the lengths of strings here would represent all possible lengths attainable using 3 or 5 blocks of 3 or 5, which is 3 or 5 cent stamps. How do we solve and find out what is the largest stamp value that cannot be attained? Okay, so how about if we build a minimal DFA for this one? This is an observation I made saying when the minimal DFA cannot flare out from one state because it has only one symbol in the alphabet, so it will be a stick with a lasso at the end. So you cannot make 1 cent, you cannot make 2 cents, you can make 3 cents because this RE is making this DFA. Cannot make 4, can make 5, can make 6, no 7, and 8 on can be made. So this is an actual cute way which I discovered to make postage stamp problems solvable using regular expressions. And there is a formula available for calculating these using this is the Sylvester's formula. So it is 3 times 5 minus 3 minus 5. So 3 times 5 minus 3 minus 5 is what Sylvester says is the largest stamp that cannot be made, which is 1, 2, 3, 4, 5, 6, 7. 7 cannot be made. Okay, so now suppose somebody says, I want to consider 11 cent stamps also. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Then there is no equivalent Sylvester formula. It doesn't work. But your method using regular expressions still works. And if I just execute this one, you get a different machine. So here, 1, 2, 3 can be made. 4, 5 can be made, 6 can be made, 7. The answer is still 7. Interesting. So let us leave out the 3 cents, and now it is 5 and 11. And let us say, and let's add 7. 1, 2, 3, 4, 5, 6, 7. 5, 7, and 11. So what is the deal here? So at this point, oh, it's pretty long. So we can count all the way. But there is a way to get the actual value of the stamps. It is actually the number of states minus 2. So if you take length of min MD35 of Q and minus 2, that actually is the count 13. So let us see. 13 is the largest you cannot make. 1, 2, 1, 4. So 1, 2, 3, 4, 5, 6, 7 can be made, 8, 9, 10 can be made because of the 2 5s, 11 can be made, 12 can be made because of the 3s, 13 cannot be made, and 14 on can be made. So this is a quick way to arrive at the largest postage stamp that cannot be made for any number of relatively prime stamps. So this is also held here. How about if I try 4, 3, and 9? They are not relatively prime. 2, 3, 4, 5, 6. Let's say 6 and 9. What would be the answer? 6 into 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. Star. And what is your guess? Is there a stamp value that cannot be made? Well, a quick reflection will tell you it doesn't exist. So because after there are gaps of 3, because at some point there is a greatest common divisor. So there are gaps of 3 at the end, and this is a lasso that opens up. So you cannot make 3, 4, 5, 6 can be made, 7, 8, 9 can be made, 10, 11, 12 can be made, and things like that. So the reason for choosing relatively prime numbers must be clear now, that the largest exists in general only for relatively prime number situations. Okay, I hope this was another illustration. So now we are motivated to study RE to NFA, NFA to DFA, many of these algorithms, and that's where we are going now. And so thank you.